So is LK-99 dead or not? What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had an amazing week and have a brilliant weekend in store. Now, the science news this week has continued to be dominated by the idea and the possibility that the modified lead apatite structure LK-99 may be a room temperature and pressure superconductor. And now, evidence and research that points out that it may not be. If you'd like to learn more about LK-99, its structure, and previous evidence that showed that it could be a room temperature and pressure superconductor, please check out my previous discussion with chemist Professor Simon Clark. Today, we'll be exploring whether the LK-99 saga is over, what the future may hold, and what lessons we can learn. Room temperature and pressure superconductors are one of the holy grails of science. Such a material would display zero electrical resistivity and would help to reduce transmission line losses, prompting massive energy and carbon savings. Such materials would also be invaluable when constructing fusion reactors or future particle colliders, and may even help us progress in the fields of quantum computers and superfast transport. However, replication attempts for LK-99 have been at best mixed, and new research seems to suggest that although LK-99 may be an interesting material, it is not a room temperature and pressure superconductor. So is the LK-99 saga over, or could more data tip the balance again? And what can we learn from LK-99 and the furore surrounding it going forward? To help me answer those questions and many, many more, I'm joined by another brilliant special guest, Professor Michael Fuhrer. Professor Fuhrer is an ARC Laureate Fellow in the School of Physics at Monash University in Melbourne, Australia. Professor Fuhrer directs the ARC Centre of Excellence for Future Low Energy Electronics Technologies, or FLEET Centre, and co-founded the Monash Centre for Atomically Thin Materials. Prior to coming to Monash, Michael directed the Centre for Nanophysics and Advanced Materials at the University of Maryland in the States. Michael is a Fellow of the Australian Academy of Science, the American Association for the Advancement of Science, and the American Physical Society. Michael's research explores novel materials such as graphene, topological insulators and two-dimensional semiconductors, metals, and superconductors. So who better to help me understand the hype around LK-99 and whether the journey is at its end? So, Professor Fuhrer, there's been a lot of interest and hype around the potential room temperature and pressure superconductor LK-99. It's gripped the science world and science news for a couple of weeks now, maybe 3 weeks. Before we get into some of the weeds of the latest findings, how do you see the current state of play? Can we now be fairly certain that LK-99 is not a room temperature and pressure superconductor, or at least that the evidence doesn't suggest that it is?
Yeah, I think things have changed quite a bit in the past week. I think what we know now is that there are some good explanations for the behavior that was reported in LK-99 that don't have anything to do with superconductivity. So on the balance, I would say that suggests that there's an easier explanation and that it's not a superconductor, and that what was observed is due to some other effects.
And we're gonna get into the weeds of some of those things. So there have been quite a few people. I mean, yourself, you said that, you know, on balance, the entirety of the evidence seems to suggest that there's, you know, we don't have a room temperature superconductor here, when I could get my words out. We've had other people say, you know, this is all she wrote, but we have had some mixed results as well, haven't we? So we've had some that suggest superconductivity below a certain temperature. We've had some that suggest it's all ferromagnetism. We've had some that suggest it's half levitation. So we have had a little bit of a mixed bag, and I want to jump into a couple of those. So let's dive into a couple of the new pieces of evidence that suggest that LK-99 is probably not, to start with, a room temperature and pressure superconductor. So in my previous discussion with the chemist, Professor Simon Clark, he suggested that replication attempts would come along quite quickly because of the huge implications of a potential room temperature and pressure superconductor. So that has proved to be the case. And let's focus on a preprint from the Beijing National Laboratory for Condensed Matter Physics. So let me pull that one up now. This is entitled "The First Order Transition in," I'm not going to say the full chemical symbol, but I guess LK-99, containing copper sulphide. So can you give us a brief rundown of what this paper shows and how it potentially demonstrates that LK-99 is not a room temperature and pressure superconductor? Because I think you said this was almost a mic drop moment for the issue.
Yeah, this one was really interesting. This is the one that I think kind of brought it home for me. The interesting thing about this paper is that it's not really so much about LK-99, but about this copper sulphide. And the copper sulphide is a material that is known to be in the LK-99 samples that were synthesized by the Korean group, the Q Center group.
Yeah.
And so their samples certainly have copper sulphide in them. So what this group in Beijing found is that copper sulphide goes through a phase transition around 400 Kelvin, which is the temperature at which LK-99 is thought to become a superconductor. And at that temperature, its resistance drops a lot. So orders of magnitude. So if you're in the lab and if you're a grad student and your advisor gives you a chunk of a sample and says measure its resistance, and you find that that resistance drops a lot at 400 Kelvin, you're going to say, "Ooh, there's something really cool going on here." But in this case, this is a kind of an old material. It's a mineral, and this is not superconductivity. This is just a transition between two semiconductors, really, or insulators, and one of them just happens to have a lot lower resistance than the other.
I think you mentioned that. So this is the plot they have showing that transition. I think you mentioned when we were talking offline that this is not actually new work. It's kind of lost knowledge, if you will. And this was found in a previous paper, a lovely plot here that you sent me that has conductivity instead of resistivity. So you have to kind of see it on the other side, but basically shows the same effect, I think, from 1973. So this is 50-year-old knowledge.
Yeah, that's
basically.
right. I mean, so this is something that's out there. It's not really new. It's not, I would say it's not controversial in the sense that, you can look at this old literature, this plot here that you're showing, and it shows that, yes, indeed, that copper sulphide does change its resistance a lot around 400 Kelvin. Pretty sharply. I mean, in a way that would, might fool somebody into thinking that they had a superconductor. And, that's not a typical kind of behavior. It's not just any old material that you get off the shelf. You're going to find that it's got some phase transition between two different phases that have very different resistances at, 400 Kelvin. So, and this material is definitely in the LK-99 samples. And so that looks quite convincing that there's at least some explanation for how you might get fooled that this is a superconductor when maybe it's not.
So just to kind of underline that for people, it's not necessarily, this is a scam and they didn't know what they were doing and they're trying to fake this. This is a genuine change in a material that could just explain the observations that the original authors from the Q Center had, and it's basically potentially fooled them into thinking that this is a room temperature and pressure superconductor when it's something a little bit more banal, but still very interesting.
Yeah, a lot of points there to unpack. You're exactly right. I don't think this is fraud. I don't think this is something that, was intentionally misleading. It could very, very well be an honest mistake. And in fact, a lot of people, scientists around the world, looked at this. Nobody mentioned on Twitter, for example, that copper sulphide, has this phase transition, and so and certainly there was a lot of interest in it. So it's a pretty subtle error. Error maybe is too strong a word. I mean, it's a
An oversight, maybe, if you didn't know
it's an
about it.
oversight. Yeah, it's a bit of a wrinkle, unexpected wrinkle,
Yeah.
that could explain the results. And I think it's too much to be a coincidence. Yeah.
I've also not seen anyone, anyone, I'm sure there's someone somewhere, but I've not seen much, this is obvious fraud on Twitter. And that is where you would probably see people throwing around accusations, if anywhere. And
Yeah,
I haven't really right. So people are a little bit more, unlimited on there. So I haven't seen that. So we're not saying that at all, but we are saying that potentially this transition is maybe what they're seeing in the material, because we know this material is present in LK-99. So as you say, it's very surprising if this would be a coincidence, and maybe it helps to explain the original results. Has there been any pushback to the idea that this is kind of the smoking gun that undermines this? I want to come on to the composition issue a little bit later, but I think some people have said maybe this is not quite the LK-99 sample that people have, or at least the authors synthesized initially. So maybe this is slightly an unfair test. Is that a comment that you
look,
want to jump on?
absolutely. I mean, this is this is not really a report so much about LK-99, but more a report about copper sulphide. And well, in fact, the Beijing authors did make a sample where they mixed some copper sulphide in with the LK-99, but they probably had to add a lot more than is really in the sample that in the Korean lab. And they were able to see some resistive transition, but it doesn't. It's not a proof that LK-99 is not a superconductor. It just says that there's a sort of credible alternative explanation. And once there's a credible alternative explanation out there, on balance, I think a lot of people are going to say it's more likely that than this, essentially what's a unicorn in science, to find a room temperature superconductor.
And this is kind of, I've noticed in some of your work on Twitter, some of your threads on Twitter, is that you make this point that it's very rare with these kind of materials that somebody comes up with a bulletproof proof that it's not, because that's not really how we work in science. We need that weight of evidence to show that it is, rather than trying to prove this negative, that something amazing happened on this one instance in a lab and we need to know exactly what happened. Well, no, we go on the balance of the evidence as to whether this thing is a room temperature pressure superconductor or not.
Yeah, absolutely. I mean, this is really, it's a frustrating thing about science, but it's just the reality that you can't explain absolutely everything. And there are many things where we'll never really know, or we don't know. We can't explain exactly how this result came about, that result came about. It's just, when the balance of evidence piles up, that it's maybe more likely to be something else, then we kind of move on to things that look more promising, more interesting. It doesn't mean it's not a superconductor. Doesn't mean people shouldn't work on it. It doesn't mean people would be crazy if they worked on it. They're certainly not. But I think we're not at that stage where you're going to see labs around the world still dropping everything that they're doing to work on this one thing,
as they kind of have over the last couple of weeks, which is
because it's very exciting.
Exactly. So I want to focus a little bit more on the evidence that it might not be, and then maybe we'll talk about some of the still kind of open areas. So another preprint that came out was this one, and this one is entitled Ferromagnetic Half Levitation of LK-99-like Synthetic Samples. And this seems to suggest that the levitation that we saw in the original LK-99 samples, so when we're thinking about these videos where we saw this kind of hinging behavior, that maybe this comes from ferromagnetism. Can you tell us a little bit about what this paper shows and how, again, it potentially helps to demonstrate that LK-99 might not be a room temperature and pressure superconductor? Maybe if you could give us a little introduction into what ferromagnetism is and kind of what they show in this paper.
Yeah, so ferromagnets are probably a little bit more familiar to people than superconductors. Ferromagnets are materials in which the little magnetic moments, if you will, little tiny magnets that are essentially the electrons or the atoms in the material, will line up with a magnetic field and form a magnet, just like the one that sticks to your refrigerator door.
Yeah.
So they're things that are generally attracted to a magnetic, another magnet, because another magnet will magnetize that piece of ferromagnet, and then the two will attract each other. And so, so one of the things that superconductors do is they repel magnetic fields. They're diamagnetic.
Mm.
They, in fact, exclude all of the magnetic field from their interior. And so there's this amazing levitation effect that happens with, you place a superconductor over a magnet. And people look for that, and, if you had a room temperature superconductor, you'd expect it to levitate. And so, one of the things you do is you throw it on top of a magnet and see what it does. And if it's doing something kind of funny, you think, wow, maybe that's that's a sign that we've got a superconductor. But wait, not so fast. It's not, we don't have a lot of experience with this in science. This isn't the usual test. You usually put it in a magnetometer and you very carefully measure, what is the magnetization, which direction is it?
It looks exciting it looks exciting to dump a video of this on Twitter and say, the rocks are floating has been a phrase we've seen going around lots and lots and lots. But this is not really the way that we, the smoking gun for superconductivity, as we'll kind of come on to later, what we would actually want to see.
Yeah. And so scientists had a hard time with these videos, right? Because, we're
going to talk about a couple of those later, but yes, agreed.
Yeah, we want a chart that shows you the magnetization versus magnetic field. That's the standard we're used to looking at. And so, what it does when you throw it on top of a magnet, that's not really exactly what we're used to. So, so what came out over the last couple of weeks is a couple interesting things. One, this report showed that, there can be ferromagnetic material as some kind of impurity in this LK-99 material, if you synthesize it the same way that is in the recipe that's in the reports.
Okay, I think I'm maybe understanding better. So there can be ferromagnetic sections and diamagnetic sections within the same sample, depending on how it's synthesized.
Yeah, exactly, right.
Okay.
And yeah, so not totally obvious, and it's at this point it's not exactly understood what those different pieces of material are, but at least it showed that you could have parts of the material could be ferromagnetic, attracted to a magnet, part could be diamagnetic and repelled from a magnet.
Now that makes sense, and then you get this hinging behavior where one is attracted, one is pushed away, and it starts to
and in fact they got exactly that. And they were able to show they could get their samples to do this hinging thing, and those samples did not show superconductivity, so they didn't show zero resistance or low resistance.
Yes, I think I have that plot as well. So they did the resistivity plot as well, and they show no evidence of this kind of drop to zero resistivity. Yeah.
So that was interesting. We actually kind of learned something. We learned that these videos of kind of half levitating things are not really the evidence that you might think they are. And in fact, one kind of interesting thing is that people had done amateur experiments or semi-amateur experiments on Twitter that showed kind of the same thing, that they could paste together some little bits of iron and some super glue and make something that really kind of looked a lot like a LK-99 superconductor. And wasn't, that this one here that you're showing is just made out of super glue and little bits of iron filings.
So this has got a ferromagnetic piece of iron on one side and then some diamagnetic glue on the other side, and we've got the same.
It may turn out that it's not even very diamagnetic, right? I think what's going on
just
there,
a differential though.
Yeah, it could be that there is a kind of a shape dependent ferromagnetism, that the ferromagnetism tends to line up the magnetization along a very narrow, thin sample.
Yeah,
and that may tend to put a torque on it and lift it up and kind of make it more point towards the magnet. And So yeah, it looks like well, this one is something that, it's a bit surprising until you do the experiment that it looks like, even just with ferromagnetism, you might be able to get something that kind of looks like it half levitates. Now this thing is not lifting off the magnet, so you can get a superconductor to hover in midair, well off the surface of a magnet. In fact, you can even flip the magnet upside down and have the superconductor hang from underneath, which is much more surprising behavior. So if you saw that at room temperature, you might be a lot more convinced.
So it does seem a little bit, if it were to be a room temperature and pressure superconductor, it seems a bit, I think Simon Clark referred to it as lethargic for, we might expect a little bit more than what we see here. And I think you mentioned the shape anisotropy. So I think the key line from the preprint here is, we argue that together with the pronounced shape anisotropy of the small fragments, so essentially that they're not a uniform shape in the original video, that soft ferromagnetism is sufficient. So it's not necessarily the answer, but it is sufficient. It's a reasonable alternate hypothesis to explain the observed half levitation in strong vertical magnetic fields, such as those we would see if you stuck a little scrap of LK-99 on the top of a big neodymium magnet or whatever they did in the original video. So it's reasonable to suggest that potentially what we were seeing were these ferromagnetic effects and we weren't seeing a superconductor. I should just flag up before you comment on that this is a video that was made by Derek van Gennep, just to make sure that we source that we cite the people we're using.
Yeah,
but yes, cool. This is a reasonable alternate hypothesis for the original LK-99 video. Is that fair?
Yeah, I think so. I think it at least says that you don't need superconductivity to explain it. So, again, it's sort of removing another piece of evidence that, we thought, well, superconductivity is the only way we can explain that. And now we find that, well, there's some alternative explanations that seem quite plausible. Yeah.
I think you also mentioned when we were chatting offline again, one of your additions was that maybe in this case, the crowdsourced kind of Twitter crowd got slightly ahead of the scientists on this, because I think Andrew McCallip, who was doing his Meissner or bust, trying to make this in his basement and trying to get the rocks to float for the people on Twitter and YouTube, I think he find that there could be certain iron impurities in here that could have these ferromagnetic effects potentially.
Yeah, that's right. Yeah, I think he had his samples analyzed at USC, so he did have some help from some science labs, but it looks like he got some impurities in his samples. We also get a little bit more information that they found iron in the impurities, and that there I would say that might be good or might be bad for the LK-99 proponents, because shouldn't be any iron in there. So it may be that the people who are getting ferromagnetic impurities in there are getting them from something that's slightly impure in there.
Yeah, maybe a bad synthesis job, or maybe part of the characteristics of the material.
Iron is everywhere, though. It's very hard to avoid, right? and this is it's one of these lessons that you learn when you're looking for magnetic stuff, is that just about everything that you can get your hands on, somebody poked some iron, steel tool into it at some point, and it may have a little bit of iron in it, and so it shows up a lot. It's hard to avoid, but so you have to be careful, and. Yeah, but I think it says that it's something that could reasonably get in there, and so it's something that you'd have to be careful about, and could provide an alternative explanation.
And again, we come back to, like you said, it's a reasonable alternate explanation that starts to stack up on that side. Doesn't necessarily mean it's the final word. Doesn't mean it's necessarily exactly what happened in this case. But when we are weighing these very reasonable, very serviceable hypotheses against something that is a complete unicorn, as you said, something that's completely new in science, then it's reasonable to err on this side until we see, stunning evidence of, the perfect resistivity curve and the heat capacity done and the Josephson effect and all of these kind of things that working in tandem. So I guess the pushback I saw against this paper was, again, to do with the composition. So maybe if we jump into that now. So one of the generalized themes of pushback I've seen against the preprints we just discussed and the idea that this is kind of now over is that none of these groups that are looking at LK-99 have synthesized it correctly. They haven't got the original synthesis of what the team from Korea did originally. So whatever results you show are kind of fundamentally flawed from the jump. You're looking at different materials. What do you make of those claims? And does it seem odd that different groups are getting slightly different results when reporting on these materials? So we've seen different things, like, for example, the group, I believe, in India, they believe that they saw some levels, or they saw no levels of superconductivity, but they saw some floating. We had a synthesis from Southeast University in Nanjing. They found no Meissner effect, but they measured near zero resistance at minus 163 degrees C, 110 Kelvin. So there do seem to be some differences in the replication efforts. And some people think that that's due to different syntheses and that we haven't got the magical, synthesis that they have in Korea. How do you respond to those ideas and that pushback?
It's definitely something we should consider very carefully. I think if you're an optimist about LK-99, even if you look at
you're always going to see it, right? You're always going to try and kind of make it work.
Yeah.
I guess.
Yeah, well, that there is an element of that, but I think when I should say back up a second and say that when people first looked at this report and looked at the material, immediately many people in the field thought this is a really complicated material. Its properties are definitely going to depend very sensitively on exactly what's in it, and the characterization of that material hasn't really been done to the level that you'd like to see. And so in some sense, if it's a superconductor, it doesn't matter. We just want to know, does it superconduct? And if it does, then we're going to just take it apart and really figure out what makes it tick and exactly what needs to be in there to make it superconduct.
This was something Simon Clark flagged up, by the way. He was like, some of us are not even, on the chemistry side, they're not even sure exactly what they've made in Korea. They're not exactly clear. So it's kind of hard to test, which kind of cuts both ways. You can then say, oh, well, you haven't made exactly what we said. Well, but it's like, well, you haven't told us, so we can't get the evidence that we need.
So those are two sides of the same coin, right? It's we don't know exactly what's in the material, and so if it was a superconductor, you might expect that maybe other groups can't reproduce it, or they might have difficulty reproducing it. On the other hand, if there's not really great evidence for it being a superconductor, it's something where we don't really know much about it. So it's very hard to say, oh, this is an interesting material. We don't know that this material is a metal. We don't actually know what's in it. We don't know where the copper is. We don't know if it's in the material and how much is in, which lead sites it sits in. Yeah. We don't know if there's hydrogen in there. We don't know there's sulfur in there. And all of these things are going to have a big effect on the properties. And so we're really this is not a terribly well characterized material. Sometimes, somebody reports superconductivity in some system of materials that are quite well characterized, and we know what we're dealing with. In this case, we don't know a lot about this material, and so it's difficult to say, it's still an interesting material, and if there's some report of superconductivity, we should keep looking, because it's hard to know if this is interesting. It's interesting if it superconducts, and if you're not sure it superconducts, then it may not be interesting.
I think you said at this point you wanted to flag up the work of was it Leslie Shoup?
Yeah, Leslie Shoup is a brilliant solid state chemist at Princeton. Really kind of dug into this and said, what do we really expect is going to be in this material, and if we synthesize it, what's the material that we would actually get, and raised some substantial questions about whether the Korean team had really identified what material they had, Again, these are not killer questions if the material is definitely a
Yeah.
superconductor. If it's floating 3 centimeters off the surface of a magnet at room
We can
temperature.
say we'll work out what's in it later. It works. We'll
Exactly.
come back to that later. Yeah.
Yeah, but if we're not so sure, then it raises some issues about whether this is really kind of a well understood material that could be interesting. And I think that's not clear. There have been some suggestions from some theoretical groups that this material, if you made it exactly right, the way that it was described by the Korean group, with the copper in the right place, that it might be interesting, that it might have some flat bands and some electronic properties that look like they might be interesting, but it's just not clear that that's the material that you'd make if you did this synthesis. And the work from Leslie Shoup's group looks like it seems unlikely, right? So it seems like maybe it's a different material, and so it's. I think we just don't know that much about the material. Yeah.
I think you said there's a lot of open questions. Is it hydrated? How much copper is there? Was some of the sulfur replaced with oxygen? There's a lot of open questions that they haven't kind of been covered by the original authors. How do we get to the bottom of this? Do we need spectroscopic studies from the Korean authors, and then they say exactly what they made? Do they need to be sending samples of what they say they have and what they say is a room temperature and pressure superconductor? Do they need to be sending that to other labs so that they can verify if they really believe that they've got this? What steps do they need to take to kind of get us around this ever present pushback that's going to come, that, well, you just didn't make sparkling something else rather than the champagne of LK-99? How are we going to get around that?
Yeah, no, those are all good suggestions. So much more careful work characterizing exactly what's in that structure, and there are techniques to do that, to really figure out what atoms are in there, and that would be helpful. I think if given the essentially the critiques that have come out around the work over the last week, I think that the Korean authors should be taking a hard look at really kind of the evidence that they have and how they would address those critiques. How can they eliminate the possibility that it's some impurity phase?
Yeah.
How can they
they've had really good peer review basically from hobbyists. I don't mean that in a disparaging way, but people from non-experts on Twitter, and also from experts who've kind of dropped everything and looked into this. So there's a lot of things that they need to tick the boxes on to before they come back again.
Absolutely. And in some sense, it's a lot more harsh than you would get if you just sent your manuscript to a journal.
Simon flagged this up. It would have been behind closed doors, and they'd have said, maybe go look at this just before we put out that the earth-shattering thing. But now it's out in the in the open.
But it's not a bad thing. It's out there, and there's nothing you can do about it now. And look, the goal is not to fool nature, right? It's not to have something that still continues to fool everybody, that you think it's a superconductor, but it's not, right? You want a real superconductor. And so this is showing, hey, here are the things you got to do to make sure that it's not XYZ. It's not something that is fooling us. And so they've got their work cut out for them. But if it's a real superconductor, they're going to be able to.
It doesn't matter for 3 or 4 months of extra work is that's going to be all fine in the end.
Yeah, doesn't matter at all, right? I mean, if it works in the end, then we're all good. And there's believe me, the scientific community has no problem with it working in the end and accepting it and saying, hurrah, this is great. You guys are heroes for finding this.
Exactly.
Absolutely. Yeah.
And I think it's worth flagging up at this point. Somebody said it really nicely, but there's nothing special. We obviously think of it as special, but there's nothing special about room temperature and pressure on Earth. This is obviously a barrier that we think of, but I believe there's no physical reason why we couldn't have a room temperature and pressure superconductor. It's just something we haven't seen yet. So You know, maybe we will, maybe we have one in this case, but we need to do extra work to be clear. It looks like we don't at the moment. So there have been some findings, just to kind of balance the docket, that seem to push in favor of LK-99 being a room temperature and pressure superconductor. So, for example, this preprint, which is an observation of very low resistance above 100 Kelvin in essentially an LK-99 sample. Any thoughts on this preprint? It's the one that comes with these kind of data, which seem to show a kind of drop in resistance at a higher temperature.
Yeah. Look, it's one sample, and I would just be cautious.
Yeah.
I would say that this report in isolation would not be convincing. It's interesting because it's on this material LK-99, and we have some other evidence, but it doesn't really look like what the Korean group observed. And there are a lot of important differences. They don't really see a sharp transition to zero resistance at a certain temperature. They see this very smooth, gradual, but exponential reduction in resistance, and that's not really what you expect with a superconductor. But there are known artifacts in doing these kinds of measurements that can do this. And so one, for example, is that if you have conducting and insulating regions of your sample, those insulating regions, as they become insulating, can cut off your voltage probes, and you can get this kind of behavior. And so you have to be a bit careful.
This is where an expert would know about that, you see, whereas if I look at it, oh, that looks kind of interesting. What's going on there? But then someone like yourself can immediately go, I've kind of seen this before. You know, we've had this in the lab before.
And this is the kind of thing that would be checked with peer review. And so, you know, if I were to referee this paper, I would say, hey, just, you know, go back to the lab, you know, make sure, you know, we want to see measurements on multiple samples. We want to see different sets of current and voltage probes, you know, different measurements. So some checks that you can do. And look, you know, this paper is, you know, kind of rushed onto the archive in a very short time frame. And so, you are going to see this kind of thing where it's it's not clear they did all the checks. Maybe they did, and they just didn't put them in because they didn't have time, or maybe they haven't, and that's why we need peer review.
Yeah, perfectly good explanation. So I want to get on to as we kind of go into a different section, these videos that we kind of flagged up earlier. So, you know, some of the evidence that people will point to for it being a room temperature and pressure superconductor are these videos that keep leaking out all over on the internet. What have you made of some of the kind of sometimes grainy, usually very short videos of floating rocks that have appeared on social media? There's particularly one that kind of got people very hot under the collar this week. Maybe if I turn the sound off on this, just so it doesn't, turn that down. But this one, where it seems to be a person stroking a piece of levitating material, and it seems to be kind of flux locked. They push it to the side. It seems to resist that happening. It seems to be floating above the, I guess, neodymium magnets here. A lot of people have claimed this could be flux pinning, and therefore this is a room temperature and pressure superconductor. Any thoughts on this video? It was released to the Chinese video sharing site Bilibili, and I don't know if it's anonymous. I haven't had a chance to translate the words that have gone with it, but it got a lot of people hot under the collar, including some, you know, quite serious psychommers.
Yeah, I mean, look, I know enough not to make too much of videos posted on the internet.
I was actually very surprised and a little bit frustrated by some of the big psycho. I won't flag them up because I don't think that's fair if they're not here to kind of explain, you know, what they think they saw. But some very big psychommers, that names that you would know, names with lots and lots of followers, who are like, this is amazing, this is brilliant, but I don't even know what they're floating. I don't know if they've edited the video. The video is very short, so maybe it's a normal superconductor that's been cooled down and then is levitating for a few seconds. The idea that this was taken as very serious evidence seemed
Yeah,
a
look,
little
it's
bit ahead
simple
of the
enough.
evidence for me. I don't know. I
Yeah.
mean, I'll let you talk because you're the expert on this.
Yeah, but look, I mean, if you had this thing floating on top of your magnet like this, it would be simple enough to give it to the local news team and let them film it, right? I mean, seriously,
Or at least
I'm
do it
not
for
sure.
20, 30 seconds rather than, 4
Yeah,
seconds
I mean,
looping seems very odd.
but I don't want to suggest all the things that you ought to do because then somebody will still find a way to fake them, right?
I'm going to get onto
Let's
After
just
Effects
say,
afterwards, and make it,
yeah.
make it work besides.
Let's just say wait for a report, a scientific report that's got somebody's name signed to it who's credible as a scientist in that area. I think that's the thing to do.
Yeah. I think in this case, so the idea here was this was kind of, you can see the flux locking, it's floating above the magnet, and then people were a bit more excited because if this was LK-99, then yes, at room temperature and pressure, it looks like it's floating above the magnet and also locked in place. But then again, we had our friend Derek Van Gennep came back and said, look, you could make this thing with a standard superconductor. You could cool it down. You could then stick it over the magnet. And if you wanted to remove the smoky appearance, well, you can just do that in editing, or you can run a little fan over it. And you could get something that looked very similar to this. So again, going back to your point, we really need a little bit more provenance than here's a scrap of something by an anonymous person on a video sharing website. Why are they not sending it to the local news crew or bringing people in?
Yeah, I mean, there were a couple of videos that people made where they stuck a little wire on the back of a rock, and it looks pretty convincing if you take it from the right angle and you can't see the wire. I mean, I'm not sure this one requires explanation. Let's just say there are too many too many videos on the internet that look suspicious to worry about how they made each one.
Yeah, I think you're right. If you start going down that rabbit hole, like, it never stops, right? So best to just wait until something reaches a bar of provenance and reaches a reputable agency or institution, and then we can really worry about that. But obviously, it gets people on the internet excited, and particularly non-experts. They see this floating and they think that's a really key idea that hurdle that needs to be passed, and it is, but potentially in a more strict setting. So I guess returning to the spirit of the opening question today, we talked about some of the evidence for, some of the evidence against LK-99 being a room temperature and pressure superconductor. How do you weigh all of that up, and how far have we come in the past week or two or three? What would you say is the current status?
Yeah, I should say maybe overall, I think this is it's the right question to ask, and I think it gets at the heart of the way scientists do science, and I think it's something that maybe the public doesn't understand so well, which is that scientists are incredibly skeptical, right? We look at everything with deep skepticism. Yet
sometimes that makes us look like sticks in the mud, right? And
yeah, I know. I mean,
it
sounds like the pessimistic people that go around saying nothing ever works, right? But at the same time, we're incredibly excited about scientific advances, right? So the balance between those two, the thing that's going on is that we're incredibly excited about scientific advances, but we want to make absolutely sure that they're correct. And we've been fooled many times before. And we fool ourselves. If we go around thinking, if we go around wanting something to be correct, we'll fool ourselves, right?
We've been bitten many times, so we're shy. We're shy about it now.
So it's very important that we're very skeptical about results. We think of every possible alternative explanation and explore it thoroughly. And then once all of those have been explored, then we can, pop the champagne corks and all of that, right? And so, so we're not at the champagne cork popping stage for LK-99, and it's back to the drawing board for, the original authors.
Then go put it back on ice, do a bit more work, and then maybe we'll bring it back out later.
Yeah, that's right. So, so I think, the rest of the scientific community is probably gonna, take some of that focus off of LK-99 and look at things that they think are more promising, which is what we're always doing anyway. And you know, the LK-99 authors have their work cut out for them to really come back with a convincing case, and that's where we are. I mean, I think it's unlikely, and that's the way we came into this anyway. I mean, you know, most scientists, you know, I think if you'd interviewed them the day that paper hit the archive, they would have said, yeah, well, room temperature superconductivity, it's unlikely. And that's fine. But, you know, again, it's also exciting, right? It looks plausible, and it was very exciting. And we all got to work on this really cool thing that might have been exciting for a while. And, you know, I'm sure some grad students in some labs got really great experience thinking about some new problem and doing something really cool and getting the results out fast and trying to beat their colleagues and all of that. And that's great. So we, you know, yeah, it was always a long shot. And I think it's an even longer shot at the now.
That was kind of the question I was going to ask is do you expect any more serious work to be done on this going forward? But I guess what you said is most of the scientific community will kind of move on, and the people, the original authors from the Q Center, probably have their work cut out for them now to handle the pushback that they've seen from experts and from you know, other interested parties. And they probably want to demonstrate some of the other things you note in this thread. So we want a full demonstration of the Meissner effect. We want to see the full superconductivity curve. We want to see the spectroscopic results. We want to see maybe some heat capacity results. We want to see maybe the Josephson effect. We want to see all of these things, and then come back and show us that you really did have one.
Yeah, I mean, I would say in this particular case, one of the problems is that the material science hasn't really been done on this material, and so it's just, we don't know if it's an interesting material, period. And so there's just more work that needs to be done. Yeah, I think you know, there are a lot of ways that you can demonstrate something's a superconductor. On the other hand, you know, even a couple of those really convincingly demonstrated are okay, right? I think if you demonstrate that it's got super strong diamagnetism at room temperature, you know, much stronger than any material that we know, which is what superconductors do, then it's definitely interesting. And if it's got ultra low resistance, you know, lower than copper, much lower than copper at room temperature, then that's definitely interesting. And those things weren't demonstrated. You know, what was observed was consistent with, oh, maybe part of this material is a superconductor and the rest of it's some junk, and we just got to find that tiny part that's a superconductor. And that often happens when you have a new material. You know, it's mostly junk, and then there's that special part in there. And that's fine. It's just that at this level now, I think we got to go beyond that and get to the, you know, the really convincing demonstration that, you know, it can only be a superconductor.
Yeah. I want to, so I think we've covered most of the science we need to cover. I just want to very quickly, before we finish, switch on to a kind of another layer of this. So that's the social side. So there's been an awful lot of hype around this topic, and you know, we've both been involved in that. You know, there's no clean hands there. As you'd expect with a potential discovery with such far-reaching implications, what have you made of the massive interest in this potential room temperature and pressure superconductor and the associated reporting and social media around it? Because on one hand, very, very positive that people are getting so excited about, you know, fundamental solid state physics and chemistry. On the other hand, there's been this kind of wild roller coaster of we're on, we're off, we're on, we're off, we're on, we're off, which to some extent does demonstrate kind of the advocacy that goes on in science, but is also perhaps doesn't have the kind of, what maybe the best word is conservatism and kind of damping that science has, where we kind of move slowly between these things. It's been a bit more of a kind of sloshing around. What have you made of the kind of the hype train, if that's the right term to use?
Look, I'm generally positive about it. I think that I think that you know, generally people, I think, got really excited about something that was coming out of materials science and physics and could really change their lives. And it's a, you know, it's a real possibility. So it was being hyped, but it, you know, reasonably so. I mean, it is something that a lot of physicists believe that, we will one day discover a room temperature superconductor. So it's not crazy. And I think that got people excited, and they started thinking about, what it would be useful for. And I don't think it was overdone. I think a lot of the reporting, at least in the mainstream media, I think
the mainstream was pretty good. Yeah.
A good balance, where they said, look, this is something that a lot of scientists are skeptical about, but, it's also really cool and it might happen. And it, if it does happen, it could come out of left field. And, this is, it's reasonable to look at it. And so I don't think it was that bad. I mean, I actually think it was quite positive. I think, I'm pretty active on Twitter, and this was one of the more pleasant weeks on Twitter that I've had. I have been involved in more contentious issues on Twitter, and this one was, in comparison, just absolutely completely collegial. Everybody was just.
I think you've done some studies around COVID,
very
right?
happy.
So this is I imagine this is much more friendly and cordial.
Yeah, compared to COVID Twitter, this is a dream, right? I mean, it's so everybody's happy and just wanting this wonderful thing to happen, and we're all going to live in a better world if we all get this superconductor. And people were sad that we we probably didn't, but it's it actually, I think, was quite positive, and people got a good kind of intimate glimpse into what doing the science is like, and they got the result pretty quickly, right? I mean, it could have been worse. It could have dragged out to the point where people were just bored about it and didn't care and never
nice
really
kind of rising kind of and came to a crescendo.
Yeah. So I think it was pretty good.
So my only concern is with the Rangadius retractions, and now this having come to nothing, that maybe people will start to think of this field as maybe being overhyped and under delivering. Is that a concern, or am I seeing something that am I being overly concerned about something that probably isn't an issue?
Yeah, I think it's a concern. I mean, I'm definitely worried about reproducibility and about fraud in science. I think in this case, the story is a good one. I don't think that it was fraudulent. I don't think there was any fraud involved, and I think science did a really good job in figuring out what was going on really quickly and came to kind of a reasonable conclusion.
The archive worked really well, right? And probably as intended.
Yeah. Right. Yeah. So I think the scientific community kind of worked together quite well to really figure out what was going on and kind of deliver answers, which sometimes those answers don't come. So it's good that it actually came to a nice conclusion. So I think it's a positive story. But yeah, I mean, I think there are cases where there is fraud that happens in science. I think the Diaz case is at least one where scientists were able to kind of discover that this is something that looks a little suspicious, and so there's at least an internal self-correcting mechanism there, which is good to see.
Which should give confidence, I guess, because even if this does turn out to be a fraudulent thing, it was caught within the peer review process, and it was dealt with within the field, which should give some confidence about how these things are looked at very seriously.
Yeah, that's right. I mean, and basically this whole story is about how science gets built up, that it's not just one report, that you have to reproduce things. Other people have to be able to do that too, and everybody has to agree that this is right. And I think I would hope that's the main story there, that's the way science works. Yeah,
that's a really nice message, I think. So the final question I have is just kind of where do we go from here? So I guess from pulling on some of the threads that you mentioned, I guess we wait to see if Q Center comes out with some of the ideas that or comes out with some work to push back on some of the potential other hypotheses and really does demonstrate that this is a room temperature and pressure superconductor. But people will probably, the rest of the science community will probably move on until and if they produce that work.
Yeah, I think so. I think it's going to be on Q Center. It's really going to be up to them to, if they believe in this thing, that it's pretty clear that the additional evidence that they need to provide, and so we'll just wait and see. I think probably the rest of the community, given that it's a material that we just we don't know much about and don't understand much about, we kind of have to wait for them. Yeah.
There's no point just throwing bits and pieces together and trying to work out what's going on rather than just letting them do it themselves.
Right. I mean, at this point, look, we can't say absolutely 100% for sure that this is not a superconductor, but there are an infinite number of materials out there which we can say that say the same thing, right? And so, I mean, I could say, well, what if we put, silver or gold in lead apatite instead of
copper?
You
can't prove it doesn't work. Yeah.
Right.
Yeah.
And I mean, can't prove that it's not, but yeah, we need a reason to know that that's something that we really ought to be looking at, and it's those reasons have to be really compelling, and I think we're not quite there, but that again, it's on them. They know what they need to do.
And I think you mentioned, just to give context to that, just as we come to the end, that this is not a new story for experts in the field. There have been a large number of these. I think they called them unidentified superconducting objects that we've had in the past, where we don't necessarily get a very satisfying, oh, here's what happened. They did this, then they did this, and then they measured this wrongly, and then this happened, and we fully explain it, and now we understand everything. Sometimes we just don't get that full explanation.
Yeah, it's actually a lot more common that they just kind of fizzle out over time. You wait and nobody reproduces it, but nobody explains it, and then after a couple of years, it's like, well, there was that thing back then, but I never heard anything else about it. So, and that's quite unsatisfying.
Yeah.
But that's often what happens. I think this is actually the best resolution, that this one really got worked out quite quickly, and that we have a pretty good explanation. Again, we never know with 100% certainty, but it looks pretty convincing, and so I think it's a good explanation.
Brilliant. Professor Fuhrer, thank you very much for taking the time on your Friday evening. I very much appreciate it. What have you got planned for the weekend?
Not too much. Hopefully go out and
Twitter break.
Really getting live music has really been the thing here in the winter in Melbourne. It's a great thing to do. So yeah, I'm gonna probably go see some bands, but
amazing.
Yeah, it'll be fun. No, it's great. Thanks for having me on. This has been a really nice chat, a good opportunity to kind of really dig into what's been going on the last week, and it's been a lot of fun.
No, it's been an absolute pleasure. Just as we finish, would you like to point people anywhere to understand the work that you've been doing? I guess I'll link your Twitter with some of the excellent threads you've been doing on this topic. Any other work that you'd like to flag up?
Oh, absolutely. Yeah, so if people want to read more about what we're doing here at Monash University, and in the I'm directing a center called FLEET, Future Low Energy Electronics Technologies, and it's fleet.org.au, and we're looking at totally different ways in which electronic materials can conduct without resistance at room temperature. So
really fascinating, interesting stuff. I've had a quick look.
Superconductivity, but pretty cool stuff, and it's pretty cool quantum properties of materials. So if you're interested, I'd check it out. Yeah.
It's really amazing stuff. So I definitely suggest you go over there. All of the links will be down in the description, along with some of the links to the work that we flagged up from Leslie Shoup and other people that we flagged up in this discussion. So head down into the description, and all those links will be there for you. Again, Professor, thank you very much for taking the time on your Friday evening. I very much appreciate it. Let's stay in contact, and if the wheel turns again on this and LK-99 resurrects, let's get back together and have another chat.
Excellent. Look forward to it.
It's been an absolute pleasure. Have a lovely Friday evening.
Yeah, you too.
Take care.
Bye.
Bye now. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out, and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.